Hey guys, welcome to our second video on proof by deduction. In this we're going to go through a few examples of proof by deduction. So I'll do at least 3, I might do 4, depends what I can find. Okay, so first of all then, the first conjecture that we want to prove is that the sum of two consecutive integers is equal to the difference of their squares. So, what does this mean? Well, consecutive integers are integers that come one after the other. Sum means to add up, and difference means we will want to do a subtraction. So, first of all, let's sort out our integers. So, we'll say our first integer. So our first integer is n. Then our second integer is going to be n plus 1. So what we can do now, we can actually work out the sum of these two consecutive integers. So let's change colour, let's go green. So the sum then is n plus 1, which is 2n plus 1. Now then, that's the sum of these two consecutive integers. Now we want to find their squares and then find the difference. So, if we square our first integer, so we do n squared, we just get n squared. Good times. If we then square our next integer, so n plus 1 all squared, if we expand that out, we get n squared plus 2n plus 1. Now the difference here is the bigger take the smaller. So the difference is n squared plus 2n plus 1 minus n squared. Now that simplifies to 2n plus 1, which is exactly the same as the sum of the two consecutive integers. Therefore, the conjecture, which remember is just a posh mathsy word for statement, so the conjecture is true. QED. Okay, the second conjecture. So here we want to prove that x squared plus x plus 1 is never negative. Now let's first of all think about what never negative means. So never negative means we're allowed to be 0 or positive. So we want to prove that this quadratic is either always positive or at the very least it is 0. So it's not allowed to go anywhere below 0. How do we do that? Well, complete the square. Remember, completing the square allows us to find the coordinates of the turning point or the minimum or maximum value of a quadratic. So this guy is a happy quadratic, so we're going to be finding a minimum value. Okay, So, to complete the square with this guy then, get a bit of practice before the algebra section. We want a set of brackets with an x, a square on the outside. We can keep that plus 1 for now. Now we halve the number of x that we have in the middle. So we got 1x, half of 1 is exactly that, a half. So we got x plus 1 half squared plus 1. But there's one more thing we need to do. We need to square 1 half and take it away on the outside. So we're minusing 1 half squared. Now this will become x plus 1 half squared plus 1 minus, well, 1 half squared is 1 squared over 2 squared, so it's a quarter. So we got 1 minus a quarter, and then this comes down to x plus 1 half squared plus 3 quarters. Now this has proven what we wanted to prove. This chap here at the end is our minimum value. So it's the smallest value that this quadratic can possibly take. So let's think about the implications of that. If 3 quarters is the minimum, then x squared plus x plus 1 is always, so it's always positive without exception. It never even makes it down to 0. Therefore, we've proven it. So, this is true. So, again, QED, jobs again. Okay, example 3. So this one's quite a bit trickier. The other two are very similar to GCSE type questions that we might get on those papers. This guy requires a little bit of thought. So we want to prove that root xy is less than or equal to x plus y over 2 when x and y are positive integers. So let's be careful with what we're being told then. It doesn't say x and y have to be different, so they might be the same. So first of all, we need to try and create an or equal to inequality. So for example, we could try seeing what happens if we wrote down x plus y. But x and y are positive integers. They might be the same, they might be different, they're positive integers. So all that we can say about x plus y is that it's definitely greater than 0. So that is not much use to us. So let's get rid of that. What about x minus y? So with x minus y, there's actually 3 possibilities. So let's have a look how. So there's case 1 where x is greater than y, and then x minus y is going to be greater than 0. There's case 2 where x is equal to y. So then x minus y would equal 0. And then there's the third case where x is less than y. So then x minus y is going to be negative, which is less than 0. So again, we don't know explicitly what x and y are. These are our three possible outcomes for different variations of x and y. Now, can we turn these three statements into one statement with an inequality? Well, what's going to happen if we square x minus y? So if we square that, well, if x minus y was positive, then x minus y squared is going to be positive. If x minus y is 0, then x minus y squared is going to be 0. If x minus y is negative though, x minus y squared is still going to be positive. So what we can now say by squaring this thing is that x minus y squared is going to be greater than or equal to 0. So this is a nice little stepping stone on our way to the proof. So let's now expand these brackets up. So x minus y squared is going to give us x squared minus 2xy plus y squared, which is greater than or equal to 0. Now if we go back and look at what we were wanting to prove, on one side of the inequality we just have an xy, on the other side we have an x plus y over 2. So is there anything that we could do here so that on the right hand side we have an xy term and on the left we just have an x plus y? Well, not directly, but what we can do is be a little bit sneaky here. If we now add 4xy to both sides like that, then we're actually going to have x squared plus 2xy plus y squared is greater than or equal to 4xy. Now we're getting somewhere. So the left hand side can be factorized to x plus y squared. So now on the left we've got an x plus y part, which is good because we need that. So we get x plus y squared is greater than or equal to 4xy. We can now divide through by 4. So we're going to get x plus y all squared over 4 is greater than or equal to x, y. We then need to do one more thing. Square root both sides. So x plus y squared square rooted gives us x plus y over 4 square rooted is 2, and that is greater than or equal to the square root of x, y. So there we go, we've proven it. end of brief sign. Now that one was quite tricky. It's actually from one of the Edexcel SPEXIMEN AS level papers. Okay, our fourth and final conjecture for this video. The product of any three consecutive integers is always divisible by 6. So, we don't really need to get any algebra involved for this one. I think words will do. So, let's think about it first of all. If a number is divisible by 6, then that number divided by 6 will give us a whole number. If we have a factor of 6, well, first of all, let's think of 6 as a product of its prime factors. So 6 is equal to 2 times 3. So if a number has a factor of 2, so a factor of 2 and a factor of 3, then it will be divisible by 6. So if you were to divide a number by 2 and then by 3, you are dividing by 6. So for example, if we did 18 divided by 2, we would get 9. If we then did 9 divided by 3, we would get 3, which is 18 divided by 6. So, why is this important? Well, in a string of 3 consecutive numbers, so in a chain, let's call it, of 3 consecutive, just write that as integers. So in a chain of 3 consecutive integers, we know at least one of those will be divisible by 2. Okay, so for example, if we went for the numbers 3, 4 and 5, 4 is divisible by 2. If we went for 12, 13, 14, 12 and 14 are divisible by 2. So that is always true. In a chain of 3 consecutive integers, at least one of them is divisible by 2. What about 3? Well, so in a chain of 3 consecutive integers, then exactly one integer is divisible by 3. So in 3, 4, 5, it's only 3. In 7, 8, 9, it's only 9. In 11, 12, 13, it's only 12. So in a chain of 3 consecutive integers, exactly one is divisible by 3. But that's all that we need. So we can now conclude, because we always have a factor of 2 and a factor of 3, And then there is always a factor of 6. Thus, we've proven it. So, because there's always a factor of 2 and always a factor of 3, there is always a factor of 6. So, a product of any 3 consecutive integers is always divisible by 6. Jobs again. Okay guys, hope you found this one useful. In the next video, we're checking out disproving conjectures by counterexamples, which is probably the easiest of anything else in this playlist. So, good times, hope to see you there, take it easy, take care.